Today is Manic Monday, October 11th, 2021. Today we're going to talk about the wave nature of electromagnetic waves. The wave nature of electromagnetic waves is not in dispute. The evidence for the wave nature of light waves is indisputable, okay? Light waves have constructive and destructive interference. They have Doppler effect, just like sound waves do. And they harmonize. Light waves harmonize just as sound waves harmonize. Now, the harmony we can't see the harmonization of light waves, okay? Because the frequency, the universal frequency where they're harmonized, the cosmic microwave background radiation, is at 160.3 gigahertz. And that is a radio frequency. It is too low for our eyes to sense the impact of the waves, okay? We have rods and other things inside our cornea, and they can sense the frequency of waves and distinguish between different frequencies of waves in a very narrow range, okay? You need a certain amount of energy, the light wave frequencies, okay? Now, the medium for electromagnetic waves has fallen into dispute. There was a Michelson-Morley experiment at Case Western University in the 1890s that, or earlier, and in this experiment, the Michelson-Morley sought to confirm or deny the medium nature of electromagnetic waves. So they came up negative, and since then the consensus has been that electromagnetic waves travel without a medium. As impossible as it is, okay? Physicists have chosen to prove the impossible, that a wave can have all the attributes of a sound wave, constructive and destructive interference, Doppler effect, harmonization, and can do all of this without a matter particle as the medium, okay? Now, the reason for this confusion goes back to Maxwell and his experiments on magnetism and electricity and the electromagnetic force, okay? So, because the magnetism travels, has an effect, the electromagnetic force of magnetism has an effect on iron as flux lines, okay? And we don't know, Maxwell didn't know, and Einstein didn't know, and nobody knows how the force that powers the flux lines. So it was an innocent mistake. It was an innocent mistake because of a lack of knowledge, because Maxwell didn't know what made magnetic flux lines. and physicists did not know what made electromagnetic waves, okay? So, anyway, but let's proceed that if we proceed that electromagnetic waves have a medium, just like sound waves, okay? But that this medium is, the particles in this medium are of Planck length, okay? And they're the tiniest particle in the universe, and they fill up the entire universe, and they are invincible, and there is no way we can experimentally touch them. We can't measure the energy of a single God particle one. Now, the reason for that is the same reason that we can't make transistors spaced less than an atom of silicon. Okay, we can't make transistors less than an atom of silicon because the silicon atom is as low as we can go with silicon. We'd have to use another material to get more circuits per wafer of silicon if we got close to the volume of one atom of silicon. Okay, so we can't make chips, and we can't distinguish one God particle one because it's beyond our sensing modes. Okay, but because light waves have no rest mass, they must propagate in a medium that has rest mass, because light waves have momentum. And it is that momentum that our rods inside our eyes, it's that momentum of the medium of electromagnetic waves that we sense at the back of our eyes. We sense the momentum of the medium. Also, that light waves have, also that light waves have momentum, okay? Massless photons, okay? Because these people think, physicists think that light waves have wave-particle duality, okay? Well, what they say is if you experiment with it one way, it's a wave. And if you look at it another way through a double slit, then it's a particle. So that's where the photon, the imaginary photon, came into being. It's like the minimum amount of wave, electromagnetic wave, medium momentum energy that can be measured. Okay, so the wave nature of light is indisputable. That light waves have momentum is indisputable. Now, and light waves have no rest mass, okay, which means that they're massless. Well, a massless particle cannot exert momentum. So therefore, we are left with a matter particle, a tiny, tiny matter particle of Planck length or tinier, that electromagnetic waves propagate in, and as a result of propagation in this particle, light waves exhibit momentum when they strike a surface. For instance, there are designs, if you could make sails, very thin sails, very large sails, solely from the solar radiant light energy. I mean, light used in the sense of electromagnetic waves, all the frequencies of the radiant energy of our sun. If you could catch those, the momentum from those electromagnetic waves, a spaceship could be powered out of the galaxy, okay? So there's no doubt that light waves have momentum, okay? So, and there's no proof that light waves do not travel in a medium. We define the God particle 1, the GP1, as the tiniest particle of mass in the universe, and of Planck length. Now, Planck length is a contrived number. I guess it has to do with the highest recognizable frequency of light. Okay, so it probably has something to do with the size of the electron. Okay, so I don't know the exact details how Planck came up with this Planck length, but I guess the idea is that you can't have a frequency, a frequency length, a wavelength less than the, now this is just a guess, a wavelength less than the diameter of the electron, okay? So anyway, we have this number, Planck length, okay? And it's a very tiny particle. And I aptly named this particle the God particle because we can't build a universe out of nothing, okay? We have to have something to build the universe, okay? So God filled the universe with these GP1s, okay? And then somehow our universe developed a finite volume, okay? Or God kept pumping these GP1s into a universe of finite volume. In any event, we know that our universe has energy and matter reflective edges. Now, the reason we know this is because of a discovery in the 1970s, after 25 years of research, the cosmic microwave radiation was discovered. And the cosmic microwave radiation is isotropic, the same in all directions, okay? So anywhere you look, if you look at a blank spot, you're going to come up with 160 with 160.3 gigahertz frequency, okay? And it's coming to us from all directions. Now, the only way it can come to us from all directions is if it's reflected off the edges of the universe, okay? Because our universe makes X-rays, makes gamma rays, it makes radio waves, it makes thermal waves. Okay, so there are all sort of waves that our stars produce and our planet produces. So unless those waves go to the ends of the universe and come back, they can't harmonize to one frequency. They, in other words, the universe can't send back to us from its edges the same frequency from all directions unless the gamma rays have gone there and come back, gone there and come back, and in the process of going there and come back, they redshifted until they can redshift no more. Okay? So, anyway, we got the cosmic microwave radiation, and the only way that it can exist is if the universe is finite and if the edges are reflective. Okay, now, another thing that's not clearly defined is energy. Okay? So, in Newtonian physics, in order for a particle to have momentum, it has to have a velocity and it has to have mass. Okay? So, a photon cannot have momentum. Okay? So, therefore, the particles in which electromagnetic waves propagate must be made of matter, because only matter can have momentum. Okay? And once we get that concept that the God particle ones, as they speed up, they have momentum. Okay? And once we get the concept that the universe is finite in volume, okay, and infinite in age, okay. Now, the universe must be infinite in age because the half-life of the proton sac is a quadrillion times a quadrillion times a quadrillion times a quadrillion years. Okay, that's a very long time. Okay, and since no one can say when any individual proton was made, that proton could have been made a quadrillion times a quadrillion times a quadrillion times a quadrillion years ago. Okay. So, and also physicists do not know exactly how a proton sac is made. Okay, now, we grow our universe from the God particle ones. Under pressure, the God particle ones forms strands similar to carbon fibers, except at Planck length. So this gaseous strands formed from God particle ones hooking together. And then the strands got woven into strings, and then the strings got woven into sacs. And the smallest sac that we have technology to measure is the electron neutrino. The electron neutrino is 1/1,000,000th the size of an electron. Okay. And the electron must be a sac also, and nucleons must be sacs. The reason they must be sacs is because nucleons and electrons are mass energy vessels. They transport both mass and energy, and they can hold this energy permanently, okay? And we know this because when a positron meets an electron, okay, and the difference between a positron and an electron is their charge. a positron is identical to an electron, but they have a different charge. And the reason they have a different charge, I deduce at this time, is because these matter sacks, the nucleon matter sacks, the electron matter sacks, and the neutrino matter sacks, okay, they have a spin, okay? And the best way to think of these sacks is as little dynamos, okay? So they're little dynamos, and then there's a charged particle, like an electron, but near Planck length, okay? Like the electron neutrino, okay? So for our purposes, magnetic flux lines are the result of electron neutrinos skipping around. In other words, an electron sac has a spin, and it has these electron neutrinos at 1/1,000,000th the size of an electron spinning around it. Okay? And then the proton has has a spin and has these electron neutrinos spinning around it. And the result of this is that one side of the spinning proton sac accumulates more electron neutrinos than the other side, okay? So if you look down on the north pole of a spinning matter sac, let's say it spins clockwise, and that's a matter sac, okay? Because the north pole has a charge, okay? And then if you look down on an antimatter sac, on the north pole, it's spinning clockwise. Now, this difference in spin relative to the north pole of a proton sac or an electron sac, okay, gives it a different charge. So if you change the spin of a proton sac relative to its north pole, then you create an antiparticle, okay? Now, physicists give us that energy pulls protons and antiprotons out of vacuum, okay? This is impossible, okay? You can't pull a matter sac out of vacuum. A matter sac has to be minted, okay? Our neutrons and protons that we have today were minted inside stars. And what happens is there's a process inside the Earth. The Earth pulsates every 26 seconds. Our sun pulsates at 0.3 hertz. Okay, that translates to one pulsation every 5 minutes and 31 seconds. Okay, and as the sun pulsates, okay, heat is extracted from the core. And as it decompresses, okay, the core cools, okay? And then the easy way to describe it is that our sun has two furnaces. It has the fusion furnace making helium, and it has this extraction of heat from the core. Okay, the reason we know this is that in 5 billion years, our sun will show a white dwarf. So half the mass of the sun is going to blow off during the red giant phase of our sun, and what will be left will be a white dwarf. And that white dwarf will have about half the mass of the sun, and it will be about the size of the Earth, and it will be 200,000 times more dense than the Earth, okay? The only way to get matter to that density is through the Siemens refrigeration process. You compress matter, and it gets hotter. Okay, you take heat out of it, and you decompress it, and it gets colder. Now, the next time you compress it, it's going to be a little bit denser. So through 10 billion years of compression, making the center hotter, taking heat out of it into the outer core, decompression, cooling. Okay, you do that for 10 billion years and you get a white dwarf. That's 200,000 times more dense than Earth. You do that with a bigger star, 9 to 29 solar masses. Excuse me. 9 to 29 solar masses. You do it with a bigger star, and you end up with neutronium. Now, neutronium is 100 trillion times more dense than Earth. So if you could fit 100 trillion Earths inside the volume of the Earth, you would have a black hole. Well, actually, you would have a neutronium ball. Okay, so I won't try to calculate the solar masses in a neutronium ball the size of Earth that has 100 trillion Earths inside that volume. Because I can't think very quickly, okay? But I'll make the calculations. I've made the calculations, but I'll tell you the results some other time. Anyway, so neutronium has density, the neutronium of a neutron star has density of 100 trillion Earths in the volume of Earth, okay? That's very dense, okay? Now, once you get above 2.16 solar masses of neutronium, the neutronium develops an event horizon. What that means is that the cosmic microwave radiation tells us that the universe is finite, and it tells us that the God particle ones are under pressure, okay? Because they got to bounce back from the edges of the universe, and you have this bounce. They're always compressing and decompressing 160.3 billion times a second. 160.3 billion times a second. GP1s, these tiny particles of Planck length, compress together, and that's one part of an electrical magnetic wave, and then they decompress. That's the other half of the electromagnetic wave. So these cycles, compression, decompression, occur all the time. Well, the net result of that is there's a positive GP1 pressure throughout the universe. Now, what a black hole does, once you get above 2.17 solar masses of neutronium, once you get above 2.17 solar masses of neutronium, the neutronium at 300 trillion degrees below absolute zero. Now you say, Adoni, how can you say that neutronium is at 300 trillion degrees below absolute zero? Well, to physicists, the absence of electromagnetic waves is absolute zero. Okay? So physicists cannot measure temperatures below absolute zero because absolute zero has, if there are no electromagnetic waves, you don't know if it's 10 degrees below absolute zero or 300 trillion degrees below absolute zero, as I say that neutronium is. Now, the reason I say that neutronium is at 300 trillion degrees below absolute zero is I take the multiple of Earth's density, okay? Now, I hope you haven't forgotten, but through the Siemens, the only way you can compress matter to 100 trillion times Earth density is through the Siemens refrigeration process. Compression, heat extraction, decompression, cooling. Compression, heat extraction, decompression, cooling. Okay? So, and you do this for 10 billion years, and for our sun, you get a white dwarf. Now, the greater the pressure means the greater the compression, the greater the heating, the greater the heat extraction per unit of time. And so the bigger stars burn quicker and they create denser objects. So that's where we get the neutron star from. And then once you get above 2.17 solar masses of neutronium, the neutronium ball develops an event horizon because it's, okay, so I multiply the multiple of Earth density by 3 times, and that's how I come up with minus 300 trillion Kelvin or Adoni degrees, okay? Because I am the first in the world to postulate temperatures below absolute zero. And my measuring stick for temperatures below absolute zero for compact objects is the multiple of Earth density. So a white dwarf with 200,000 times Earth density, I say, is at minus 600,000 Kelvin Adoni degrees. Adoni degrees, okay? I'll leave you with Adoni degrees below absolute zero, okay? And I leave you, I hope you found out how to measure Adoni degrees. You take a compact object, you take its density relative to Earth density. You find what the multiple is. For instance, neutronium in a neutron ball of a neutron star is at 100 trillion times Earth density, okay? You multiply that by 3, and you discover that the core of a neutronium star, the core is at minus 300 trillion Adoni degrees below absolute zero. Talk more next time. Bye.